Previously, we found the electric field intensity due to an infinite line of charge along the z-axis using this equation. You recall that it was very difficult to perform this integration. We're going to redo this problem using Gauss's law and take advantage of the symmetry of the problem with a cylindrical Gaussian surface that's shown here. In this example, we'll see that you don't need to enclose all the charge with your Gaussian surface to determine the electric flux density field. After we work through this problem in detail and you have a good mental model of the situation, you'll be able to go back and determine the electric flux density field in just a matter of a few seconds. Before we do that, I want to make a comment about Gauss's law. It should not be a mathematical abstraction to you. You should not have to memorize the equation. If you have a mental model now of charge and electric flux, you should be able to just write down Gauss's law. If you have a closed surface and you integrate d.ds over that closed surface, it will tell you how much electric flux is leaving through that closed surface. We know that electric flux comes from charge, and for every 1 coulomb of charge inside the closed surface, 1 coulomb of electric flux will go through that closed surface. So that is the mental model you should have that gives you Gauss's law. Here is another view of our infinite line of charge from the side and looking down from the positive z-axis, indicating the electric field lines and the cylindrical symmetry. Also shown is the Gaussian surface from the side and from the top. Previously, we argued that the field due to an infinite line of charge has cylindrical symmetry. If you put a test charge in here, it won't feel a force in the z direction, which is up or down, or in the phi direction, which is in or out of the page. The only direction it will feel a force is in the rho direction, directly away from this line of charge. So the electric flux density field only has a rho component. If you move in the z direction, up or down, the force won't change. So it does not depend on the variable z. If you move around the line of charge at a fixed value of rho, so you're moving in the phi direction, again, the magnitude of the electric flux density field doesn't change, so it does not depend on phi. The only variable it depends on is rho, the distance you are from the line of charge. So this is the form of our electric flux density field. This is just a view from looking down from the positive z-axis, illustrating the cylindrical symmetry of our electric field. We will pick a Gaussian surface that matches the symmetry of our electric flux density field, so we will pick a cylinder. So looking down from the top of the cylinder, we will have a radius of rho for the cylinder. Looking from the side here, we see the side of the cylinder, and let's give it some arbitrary length L in the z direction. This example will illustrate that the Gaussian surface does not have to enclose all the charge in order to determine the electric flux density field. We now apply Gauss's law to our Gaussian surface. So we'll integrate over the top, the bottom, and the side of our cylinder. And the charge enclosed will be the line charge density times the length of the line that's inside our Gaussian surface, or L. So the charge enclosed is rho sub L times L. We chose a Gaussian surface that matches the symmetry of our electric flux density field. So no electric flux goes through the top surface or through the bottom surface. So this integral is 0, and this integral is 0. So for D, let's substitute in our form of the electric flux density field. And to go over the side surface of the cylinder, to go around, you're going to integrate phi from 0 to 2 pi. And in the z direction, from 0 to L. So let's assume we place the bottom of our cylinder on the XY plane. So integrating in the Z direction from 0 to L. On the side of the cylinder, the magnitude of D is constant, so that can be moved to the left of the integration. The dot product of the unit vector in the rho direction and D sub S will just give us the surface differential magnitude in the rho direction. If we're on the surface of a cylinder of radius rho and phi changes by the amount d phi, we sweep out an arc of length rho d phi. And if we move in the z direction a distance dz, then we define a differential surface of area rho d phi dz. Now we'll work through this once, but this is just the area of the side of a cylinder. So it's 2 pi rho times L. And in the future, you don't have to go through all the steps of this integration. Just recognize that this is the area of the side of the cylinder and write it down. Since on the side of our cylinder rho is constant, we can move rho outside of the integration. And I rewrote this integration in terms of the phi and z component. So this integration will give us a phi evaluated at 0 and 2 pi, which is just 2 pi. So we're left with the integral of dz from 0 to L, and that's just going to be L. So this integration is just the side area of our cylinder. We have our charge enclosed, rho sub L times our electric flux density field times 2 pi rho L. And the L's will cancel on the two sides. Solving for the electric flux density field, we get the line charge density rho sub L over 2 pi rho. Since the electric field intensity is the electric flux density field divided by the permittivity of free space, we can solve for the electric field intensity. The resulting electric field intensity is rho sub L over 2 pi epsilon sub 0 rho, and it's in the rho direction. Now that we've gone through this in detail, let's go back and see that we can quickly get the electric flux density field. Looking at our Gaussian surface in the shape of a cylinder, there's no flux coming out the top or bottom. The flux only comes out the side. It has the same magnitude everywhere on the side, so the flux leaving the Gaussian surface will just be the electric flux density field on the side times the area of the side of the cylinder. So that's d sub rho of rho. The area of the cylinder is the circumference, 2 pi rho, times its length. The charge enclosed will be the line charge density rho sub L times L, the length of the line that's inside our Gaussian surface. Solving for our electric flux density field, we get rho sub L over 2 pi rho. So in about 10 seconds, we can get the electric flux density field.